Hi everybody. Many mechatronic systems can be split up in so-called basic systems. Well, this is video number 3 in a series of 3 videos about these basic systems, and in this video we are going to discuss so-called special systems. What kind of special systems we are going to discuss is the constant factor, it's an easy one, and it is the delay. Well, the constant factor, I said it's an easy one. It's a relationship between output and input with a k, a constant factor over here. So y equals k times x. And that gain could be, for instance, in a mechanical system, a transmission ratio, or in an electronic system, a gain, for instance, between 5 volt and 24 volt. But it could also be a transformation from a speed in RPM towards a speed in radius per second. So gains are everywhere in your mechatronic system. When we transfer that mathematical model in the time domain towards the S domain, we get the same situation. We get y is k times x. So the transfer function y over k equals h, which is that constant factor k. So it's purely, again, a constant factor. And when we transfer the S domain towards the frequency domain, well, then we get the same transfer function in the frequency domain, which says that h is k. That means that the gain is constant for every frequency and the phase is 0 for every frequency. Why is it 0? Because this gain is a positive value, it's a positive real number, which is in the complex plane situated on the horizontal or real axis. So that vector towards this point makes an angle of 0 degrees with the real axis. So my phase is also frequency independent and it's 0. And of course, when we plot a Bode plot and the amplitude plot, we are going to express it in dB. So we take 20 times the log of k. All right, so what we discussed is, well, the gain is frequency independent for all frequencies. It's constant, a factor of k, and also the phase is frequency independent and it's 0. So it's an easy one when we plot the Bode amplitude and phase plot because the gain is constant at this level, 20 times the log of k, and the phase, as we discussed, is always 0 for every frequency. We can also look to the Nyquist plot, and the Nyquist plot is nothing more than just a point on the real axis. And that's why, because the gain is constant for every frequency, and we have discussed that in a Nyquist plot we only plot the end of the vector, so it's just a dot at this point k, nothing more and nothing less. In the S domain, the transfer function is still k, but there's no numerator or denominator with an s in the expression in this fraction, so it's no pole, there is no pole, there is no 0, so it's really an empty PZ plane, so an empty S plot. Well, now let's look to a more interesting special system like a delay. In a delay, we delay the input signal by a delay time Td, and that can be expressed by this mathematical expression y as function of t is equal to x as a function of t minus Td, which means that the input signal is shifted a time Td, and Td is my delay time. When you transform this expression to the S domain, you get a rather different expression. And it says y is equal to e to the power minus s times Td times the input signal, xs. S is the Laplace operator, Td is the delay time. So it's e to the power minus std. And e to the power minus std is the transfer function for a delay. It's h, which is y over x. And when we transform that to the frequency domain, we get that the transfer function in the frequency domain is e to the power minus j times omega times td. Well, how can we transform this in a amplitude and in a phase? Well, this is um, the um, the Euler expression of a complex number. And in that Euler expression, the amplitude is always the factor in front of the e, which is 1 in this case, and the phase is everything in the exponent except for the j. So it's minus omega times Td. So again, the amplitude is 1. It's the one which we can't see, but which is in front of the E. So the amplitude is 1 or 0 dB. 20 times the log of 1 is 0. And the phase is frequency dependent because it's minus omega times Td. So the amplitude is constant for every frequency, but the phase is frequency dependent. It's minus omega times Td. Well, in what situations do we have delays? In every digital system, there are delays because there we have sample and calculation times. So we have delays between the input and the output. And for instance, in physical systems, like in a thermal application like this, and where we have a heating system over here. So here is my actuator, and here is my temperature sensor. So there is a delay in actuating and sensing the temperature. Okay, let's go to the Bode diagram and to the Nyquist plot. We have said that the transfer function is equal to e to the power minus j omega times Td. So the amplitude is 1 and the phase is minus omega times Td. So in my Bode amplitude plot, my amplitude is always the same. It's 1 or 0 dB. But my phase plot, as we have discussed, is frequency dependent because it's minus omega times Td, and the omega is in that phase. And probably you expected a straight line because when omega increases, the phase will become negative or negative, more negative, so it will decrease. But remember, on the horizontal axis in the Bode plot, it is plotted in a logarithmic scale, and that's why the curve looks like this. So when you have a Bode plot with a phase which has this kind of curve in it, then you know for certain there is a delay in your system. Well, how does it look in a Nyquist plot? Well, what we have seen is that when the omega increases, the phase decreases. So we are looking to a plot in which the amplitude is always the same, it's 1, and when the omega increases, the phase keeps on decreasing and decreasing and decreasing. It decreases, it starts from 0 and it decreases up to minus 2 times p, and it goes even further to minus 4 times p, etc., and it keeps on decreasing. And the only curve which has that kind of behavior is a circle. So the polar plot, Nyquist plot, is a circle with an amplitude of 1 and starting point over here, and then it keeps on decreasing and decreasing. So it keeps on running in that circle form. So when you have a Nyquist plot which has this kind of behavior in it, you're certain you have a delay in your system. Well, that was all about basic systems. Thank you for watching. Thank you for watching these 3 videos, and I see you next time.